Hello and welcome back. Today we'll get into section 4.4 on some of the properties of rational functions. So a rational function has the basic format r of x is p of x over q of x, where p and q are polynomials and q is not the zero polynomial. So unlike the polynomials where our domain was just negative infinity to infinity, our domain here is anywhere except where q equals 0. And there are basically three types of asymptotes that we can see on a rational function. You can see horizontal, oblique, or vertical asymptotes. So the idea of an asymptote, it's something that the graph is getting close to. It's a line it's getting close to, even though your graph is actually a curve. So if as our inputs go to infinity or to negative infinity, our outputs approach some limit L, then y equals L is a horizontal asymptote of R. If as x approaches, instead of infinity, some constant c, absolute of R goes to infinity, x equals c is a vertical asymptote. We're still talking about of R, of course. If as x goes to, again, infinity or negative infinity, so left or right forever, if our function starts looking like linear ax plus b, a being non-zero, then y equals ax plus b is what's called an oblique asymptote of R. Alright, so how to actually find these asymptotes? We'll start with the vertical asymptote. this condition is important. Our function has to already be in lowest terms. Then we could say for all c such that q of c equals 0, x equals c is a vertical asymptote. And it's really the idea of limits that are getting there. So for example, if we look at f of x is 5 plus x over x minus 7, this is definitely in lowest terms. I don't have any common factors top and bottom to simplify this fraction any further than it is. So then anywhere that would make this denominator a 0, I have a vertical asymptote, so we just use a let line. Let x minus 7 temporarily equal 0. So pardon me, x equals 7 would make us divide by 0. That would push our absolute value of f towards infinity as we got very close to a 7. So if I have something very close to 7 minus 7 itself, I get a very small difference, a very small number. If you're dividing by a small number, your result gets big. Again, just think of just a basic one. Start dividing by smaller numbers. Your answers start getting bigger and bigger. So just sort of a limit idea here. Dividing by a very small number, our absolute value starts blowing up. So then x equals 7 is a vertical asymptote, usually abbreviated VA. I'm not saying 7 itself. We do need both sides of the equation. X equals 7 would be a vertical asymptote. 7 by itself is not anything, not an asymptote. If we have g of x is x minus 2 over the quantity, what did I have? X squared minus 10x plus 24. First, I want to check to see if this is in lowest terms. So I'll hang on to the x minus 2. I'll factor that denominator. I'm multiplying to a positive. So either plus plus or minus minus. The fact that I'm adding to a negative says it's minus minus. And 4 and 6 will get us there. We'll multiply to positive 24, add to a negative 10. So no simplifying to do on our fraction, so then we just let that equal 0. Let x minus 4 by x minus 6 equal 0. So then x equals 4 or x equals 6. Those are the two things that would make us divide by 0. So those are the two vertical asymptotes. X equals 4, x equals 6, two of them. Okay, so again, I try to do some factoring. I can't factor that denominator, so I can't do any simplifying. H is already simplified. So then we use our let line, let x squared plus 4 equals 0. X squared is negative 4. Square to both sides. And I get kicked out of the real numbers. If you get kicked out of the real numbers, that means you have no x values that would make our denominator 0, therefore no vertical asymptotes. And one to watch out for, m of x is difference of x and 5 over the quantity x squared minus 3x minus 10. Don't forget, check to see if your function is fully reduced before you proceed. So I'm looking to factor that denominator. I'm looking to multiply to a negative, so one of each sign. I'm looking to multiply to negative 10, add to a negative 3. So it sounds like a positive 2 and a negative 5. We'll get both those jobs done. But then this will simplify to 1 over x plus 2 for all x not equal to a positive 5. If we let x equal positive 5, then we have a 0 over 0 problem. That's something we handle in the next section, but for now all we have to know is that we can't use 5. So as far as for vertical asymptotes, I just use the reduced version of that denominator. So we just let x plus 2 equal 0. So x equals negative 2 is our only vertical asymptote. It's only one vertical asymptote in that guy. So notice on all of these, as far as vertical asymptotes, I don't care what would make the numerator a 0, only what would make us divide by 0. All right, so let me give you one to sort of try out. I'll put the problem down and ask you to pause the video, give it a spin, unpause the video when you're done, see if you found the vertical asymptotes. Okay, welcome back. So hopefully you first checked to see if you could do any reducing, any simplifying of our fraction. So upstairs we're multiplying to a negative 12, one of each sign, adding to a negative 1, so positive 3 and negative 4. Downstairs we're multiplying to a negative 6, so again one of each sign, adding to a positive 1, so that would be then a positive 3 with a negative 2. So our simplified n of x is x minus 4 over x minus 2 for x not equal to a negative 3. So we still can't use the negative 3. So then as far as our vertical asymptotes, our let line only takes into consideration the simplified fraction. So x equals positive 2 would be your only vertical asymptote on that one. So next up we look at horizontal and oblique asymptotes. And this one's going to the next section of paper out. There we are. So the idea here, we're going to divide it out and let x approach infinity. Anytime we're looking for horizontal or oblique asymptotes. So we'll start with f of x is x squared plus 2x minus 4 over the quantity x plus 5. So if I'm looking for horizontal and oblique asymptotes, I'm just dividing this out. Make sure you're using a division sign. A square root sign is not the same as a division sign. Those mean two completely different things. Make sure you're not trying to use them interchangeably. All right, no terms missing on either of these, otherwise we would have to have filled in the missing zeros. So x times a positive 2x, x times positive 1x, would match us up to the positive 1x squared. So x by x is x squared, x by positive 5, positive 5x. And when you're doing long division, after you're done multiplying, you're on to subtracting next. So we have a negative 3x left over. We'll bring down the next contestant there, our negative 4. And I look at what I would multiply x by to hit a negative 3x. That would be then a negative 3. So negative 3 times x is negative 3x. Negative 3 by positive 5, negative 15. And again, we flip the signs then. So the x's drop, negative 4 plus 15, positive 11. So f of x is also expressible as 1x, or just x, minus 3 plus 11 over x plus 5. Now we let the absolute value of x go to infinity. 11 over some infinitely large number. If you're getting a very large denominator, your answer is getting smaller and smaller. This term will drop to 0. So then what's left is an x minus 3. That is an oblique asymptote. That is a line that's not just a horizontal line. And again, that's just because of this limit. The limit as x goes to infinity of 11 over x plus 5 is 0. It would drop that term off. Now this one, we're looking at sort of the rational function version of a proper fraction. We have a smaller degree in the top, degree of 1 upstairs, degree of 2 downstairs. When that's the case, there is no dividing to be done. It's already in its simplest form. So as x goes to infinity, this whole thing then is going to approach 0. So y equals 0 is a horizontal line, so this is a horizontal asymptote. So be on the lookout for that. If the degree at the top is smaller than the degree at the bottom, we don't need to divide. It's already divided out for us, and basically we just have sort of again the cousin to the proper fractions in the real number world is what we're looking at here in the rational world. So h of x, x to the fourth minus x to the third plus 2x squared plus 1 divided by x minus 2. We'll put our x minus 2 outside. X to the fourth minus x cubed plus 2x squared plus 0x plus 1. And we'll start 2 places in. X by x cubed is x to the fourth minus 2x cubed. We flip the signs, and we have a 1x cubed left over. However, here I'm going to go ahead and stop looking for asymptotes. Asymptotes, remember, are linear in nature. This is nonlinear. The third power there tells me this is nonlinear, therefore no horizontal asymptote, no oblique asymptote. We may or may not have a vertical asymptote. That's not what we're asked to find on this one. Okay, so one more of these to kind of take a look at. I'll do m of x is worth 8x squared minus 3x plus 7 over the quantity x squared plus x minus 2. So if I'm looking for horizontal or oblique, here the degrees match, so I can do my division. Just like in your regular rational number problems in the rational functions, top number inside, bottom number outside. Except instead of number, it's algebraic expression. Okay, no missing terms on either of them, so I didn't have to fill in any placeholder zeros. I'm looking at what I'd multiply x squared by to hit 8x squared. That would be a positive 8. So we'll multiply it out. 8 by x squared, 8x squared. 8 times positive 1x is positive 8x. 8 times negative 2, negative 16. And we're subtracting, so we flip all 3 of those signs, including making that 16 into a plus. So we have negative 11x plus 23 left over. So now m of x is expressible as 8 plus negative 11x plus 23 over our original divisor. And just like before, if the degree at the top is smaller than the degree at the bottom, it will go to 0. So what's left is this, so y equals 8. That is just a horizontal line, so that is a horizontal asymptote. Alright, so in 4.4, I would recommend 114 all, 15 to 55 on the odds, 63 to 66 all. And again, I'll try to grade a similar one for the fans of my math lab. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.